Okay, good evening, everyone. This is the fifth live interaction session on of soil mechanics, geotechnical engineering one. I have already started the recording and the meeting, but since no one has joined, it has been already past 5. I'll be starting with the dictation of the questions in this assignment. As and when anyone join, I'll be allowing them in the meeting and they'll be writing the question from the current assignment problem. So I'll start with the questions. This has many numericals are given, less number of MCQ and MSQ in this assignment. Okay, so the first question is, so this is the fifth week live session, and the topic for this session is Boussinesq theory and vertical stress distribution. This assignment has overall 20 questions. Okay, so the first question is, according to Boussinesq theory, the soil mass is. According to Boussinesq theory, the soil mass is. The options are homogeneous and isotropic. Homogeneous and anisotropic. Heterogeneous and isotropic. Heterogeneous and anisotropic. I repeat the question. According to Boussinesq theory, the soil mass is. The options are homogeneous and isotropic, homogeneous and anisotropic, heterogeneous and isotropic, and heterogeneous and anisotropic. I'll go to the next question. At constant r, that is r is the radial distance from the point of application of the load. At constant r equals to 1 unit, the vertical stress is maximum at z equal to, z means the depth, r is the radial distance and z is the depth. So when r equals to 1 unit, constant 1 unit, what will be the uh, value of z, depth at which we will be obtaining the maximum value of vertical stress? The options are, so the options are 1.225, 0.1225, 2.124, and 1.625. At constant r, that is r equals to 1 unit, the vertical stress is maximum at z equal to 1.225, 0.1225, 2.124, or 1.625. Next question. At zero radial distance, the value of Boussinesq influence factor is. At zero radial distance, the value of Boussinesq influence factor is. That is when r equal to 0. The options are 0.647, 0.478, 0.888, 0.239. At zero radial distance, the value of Boussinesq influence factor is 0.647, 0.478, 0.888, or 0.239. Next question. A circular area of 7.5 meter in diameter on the ground surface carries a uniformly distributed load of 3 kN per meter square. Find the intensity of vertical pressure below the center of the loaded area at a depth of 6 meter below the ground surface. I'll repeat the question once. A circular area of 7.5 meter in diameter on the ground surface carries a uniformly distributed load of 3 kN per meter square. Find the intensity of vertical pressure below the center of the loaded area at a depth of 6 meter below the ground surface. The question is asking to find the vertical pressure at directly below the center of the loaded area, depth of 6 meter. Next question. A circular area is loaded with a uniform load intensity of 100 kN per meter square at ground surface. Calculate the vertical pressure at a point P, so situated on the vertical line through the center of the loaded area, that the area subtends an angle 90 degree at P. Repeat the question once. A circular area is loaded with a uniform load intensity of 100 kilonewton per meter square at ground surface. Calculate the vertical pressure at a point P situated on the vertical line to center of the loaded area such that the area subtends an angle of 90 degree at the point P. Next question. A concentrated load of 200 kilonewton acts at the ground surface. Find the intensity of vertical pressure at a depth of 10 meters below the ground surface and situated at the axis of loading. What will be the vertical pressure at a depth of 5 meters and at a distance of 2 meters from the axis of loading? So in the first part of this question, we are going to find out the vertical pressure directly below the center, that is directly below the concentrated load at the axis of loading at a depth of 10 meters. In the second part, we are going to find out the vertical pressure at a radial distance of 2 meters from the axis and a depth of 5 meters, in which the value of the concentrated load is 200 kilonewton. A concentrated load of 200 kilonewton acts at the ground surface. Find the intensity of vertical pressure at depth of 10 meters below the ground surface and situated at the axis of loading. What will be the vertical pressure at a depth of 5 meters and a distance of 2 meters from the axis of loading? Next question. Uniform intensity of loading at the foundation level of a footing 10 meters in width and of infinite length is 100 kilonewton per meter square. Calculate the vertical pressure under the center line of the footing at a depth of 10 meters. Here we have a footing, foundation level of a building, which is 10 meters in width, and we are going to consider infinite length of this footing. And on top of it, there is a uniform intensity of loading of the magnitude of 100 kilonewton per meter square. We have to calculate the vertical pressure under the center line of the footing at a depth of 10 meters in the ground surface, in the ground. I'll repeat the question. Uniform intensity of loading at the foundation level of a building 10 meters in width and of infinite length is 100 kilonewton per meter square. Calculate the vertical pressure under the center line of the footing at a depth of 10 meters. I go to the next question. A point load of 100 kilonewton acts on the ground surface. Find the maximum vertical pressure on a vertical plane at a distance of 2 meters from the loading axis. point load of the magnitude of 100 kilonewton. A point load of 100 kilonewton magnitude acts on the ground surface. Find the maximum vertical pressure on a vertical plane at a distance of 2 meters from the axis of loading. That is radial distance of 2 meters. Now we have to find out that what will be the depth at which the pressure will be maximum, and at that depth what is going to be the maximum value of vertical pressure. So first we have to find out the requisite depth at which we can obtain the maximum vertical pressure. After that, we have to find out the maximum vertical pressure. There is a vertical pressure at that particular depth which we have obtained, and the radial distance for that is 2 meters from the loading axis. Next question. A concentrated load of 50 kilonewton acts vertically at a point on the ground surface. Compute the ratio of vertical stresses at depths of 3 meter and 5 meter vertically below the point of application of load. A concentrated load of 50 kilonewton acts vertically at a point on the ground surface. Compute the ratio of vertical stresses at depths of 3 meter and 5 meter vertically below the point of application of load. So we might not need to calculate the exact values of the load. We can also do it by uh, describing the relationship between vertical stress and the depth, and then computing their ratio. So we need to find out the ratio of the stress at depths of 3 meter and 5 meter vertically below the point of application of load. That is, there is no question of radial distance over here. Okay, next question. A rectangular area of 2 by 4 meter carries a UDL of 8 ton per meter square on the ground surface. Find the vertical pressure at 5 meters below the center and corner of the loading area. So we have a rectangular area of 2 by 4 and we have a UDL, that is uniformly distributed load. Uniformly distributed load, and the value of that is 8 ton per meter square. Find the vertical pressure at 5 meter below the center and corner of the loading area. The loading area is rectangular. Area of 2 by 4 meter carries a UDL of 8 ton per meter square on the ground surface. Okay. Next question. The vertical stress at some depth below the corner of a 1 meter by 1.5 meter rectangular footing due to a certain load intensity is 100 kilonewton per meter square. What will be the vertical stress in kilonewton per meter square below the center of a 2 meter by 3 meter rectangular footing at the same depth and same loading intensity? The vertical stress at some depth below the corner of a 1 meter by 1.5 meter rectangular footing due to a certain load intensity is 100 kilonewton per meter square. What will be the vertical stress in kilonewton per meter square below the center of a 2 meter by 3 meter rectangular footing at the same depth and same loading intensity? At the same depth and same loading intensity. So the questions still here were based on Boussinesq theory, as I mentioned in the first question. These are all questions based on Boussinesq theory, and these all need to be solved as per the concept and theory of as per the concepts and formula mentioned in the Boussinesq analysis of Boussinesq theory. Next, there is a combination of questions with respect to vertical pressure and Newmark's chart. So I'll start with the next part. This is the first part of the questions. Okay. The intensity of radial shear stress in ton per meter square. The intensity of radial shear stress in ton per meter square at a point 4 meter directly below a 2 tons point load is. The intensity of radial shear stress in ton per meter square at a point 4 meter directly below a 2 tons point load is. The options are 1.22, 0.86, 0, 1.62. The intensity of radial shear stress in ton per meter square at a point 4 meter directly below a 2 tons point load is 1.22, 0.86, 0, and 1.62. Next question. The Newmark chart is based on Boussinesq theory, Westergaard's theory, equivalent load method, or none of these? The Newmark chart is based on Boussinesq theory, Westergaard's theory, equivalent load method, or none of these. Next question. Comment on the type of foundation and soil from the given diagram. Diagram is given. It gives the type of settlement, the kind of settlement it will be found in soil or the foundation, and the type of contact pressure between the foundation or footing and the soil. So, by seeing the distribution of vertical pressure, upward pressure at the contact point between the foundation and the soil, and by seeing the kind of settlement in the soil because of the application of load on the footing or foundation, we have to tell whether we have to comment on the type of foundation and the type of soil from this diagram. I'll go to the next question. In the construction of the Newmark's chart, if the number of annular area selected is 10 and each annular area is divided into 10 sectors, the value of the influence factor for the chart is. In the construction of the Newmark's chart, if the number of annular area selected is 10 and each annular area is divided into 10 sectors, or the value of the influence factor for the chart is. The options are 0.005, 0.05, 0.01, and 0.00. 0.001. Go to the next question. Originally, the number of sectors considered in the Newmark's influence chart is. Here we are talking about annular areas and each annular area being divided into 10 sectors. But originally in the Newmark's chart, what is the number of sectors in which the annular area, each annular area is divided into? So the question goes, originally the number of sectors considered in the Newmark's influence chart is number of sectors of each annular area. The options are 10, 12, 20 or 25. Originally, the number of sectors considered in the Newmark's influence chart is number of sectors in each annular area. The options are 10, 12, 20 and 25. Okay. Next question. Similar question like the previous one. Here also we have been given the settlement and the pressure diagram. What is the kind of settlement and pressure expected? What is the kind of foundation and soil which we can guess, given that they both have this kind of pressure distribution? And as we can see in the previous one and also in this one, the pressure distribution is non-uniform. So what is the type of foundation and soil that can be guessed from the given diagram? As I mentioned before, the pressure distribution here is non-uniform. I'll go to the next question. Another similar kind of another similar kind of diagram. Here also the upper region is the settlement and the lower region is the pressure. In this diagram, we can see that the pressure distribution is now uniform. So, what is going to be the type of foundation and soil from the given diagram showing the settlement and pressure distribution? Next question, another numerical. a rectangular area 3 by 1 meter is uniformly loaded with loading intensity 100 kilonewton per meter square at the ground surface. Calculate the vertical pressure at a point 4 meter below one of its corners using the Newmark's influence chart. If Na equals to 12, number of sectors is 12 considered over here, number of sectors covered in that loading area is 12, and the influence factor we should take as the generalized influence factor, which is given in the original Newmark's chart. So using that influence factor and this number of sectors, we have to find out the vertical pressure at a point 4 meter below. In this case, the data is given actually the vertical pressure at a point 4 meter below the corner. In this case, Na equals to 12. So what is going to be the pressure? Okay, rectangular area is 3 by 1 meter and the loading intensity is 100 kilonewton per meter square. To find the vertical pressure at one of its corners at a depth of 4 meter. Na is 12. Okay, next question. A similar question like the previous one. Even here, the type of pressure is uniform. It was not uniform over here, but it was uniform over here and it is uniform over here. So, and this is the diagram of the settlement. This is how the soil is settling, or the foundation is settling on the soil. So, what will be the type of foundation and soil as can be identified from the given diagram? To comment on the type of foundation and soil from the given diagram. Okay, so this is the end of the questions. I'll be taking a break. If someone joins, they can, if someone had joined previously, they can write down the answers, and after a few minutes, I'll start discussing the answers. So I'll be joining in a while. Okay, so I'll be starting to discuss the answers right now. If anyone joins, they can carry on their work from the current running question. Okay, so the first question was, according to Boussinesq theory, the soil mass is homogeneous and isotropic, homogeneous and isotropic, heterogeneous and anisotropic. So, firstly, between homogeneous and heterogeneous soil, uh, always for vertical stress distribution, a homogeneous soil is being considered, because if we consider the heterogeneity of soil, then we have to consider the properties of the individual layers of the individual constituents of that particular soil. So, in order to simplify the theory and the concerned equations, a homogeneous soil is considered. Next, between the first two options, homogeneous and isotropic and homogeneous and anisotropic. So, if the soil is homogeneous and the soil is isotropic, that means the properties are same in each and every direction, in each and every direction of the soil mass from one particular point. And if it is different, then it is anisotropic. So obviously, for the most simplified case, a homogeneous and isotropic soil will be considered for any theory of stress distribution or vertical stress distribution. So, in Boussinesq theory, the soil which is being considered is homogeneous and isotropic. So, the first option is the right answer. According to Boussinesq theory, the soil mass is homogeneous and isotropic. Hello, anyone joined? You can start from the. This is the first question. You can start writing your answers from now, from this question. According to Boussinesq theory, the soil mass is homogeneous and isotropic. The properties are same throughout, and the properties are same in all directions of a particular point. This is the first question. Please write down the answer. According to Boussinesq theory, the soil mass is homogeneous and isotropic. It is being assumed the soil is homogeneous and isotropic. Next question. At constant r, that is r equals to 1 unit, the vertical stress is maximum at z equals to. Now, when the radial distance is 1, then it has been calculated that there is a particular value till which the graph goes up, the graph of vertical stress goes up, and then it comes down, and the maximum value is obtained at a depth of 1.225. 1.225. That is, if this is the soil surface and this is the vertical line showing the depth, then the pressure will be going like this, and then like this. So this point, the vertical stress will be the highest, and this z, if this is equals to 1, then this z will be equals to this. So I hope it is clear. Who is there in the meeting? Okay, yes. So this is the that is 1.225, the value of z at which we can obtain the vertical stress, maximum vertical stress. Okay, next question. At zero radial distance, the value of Boussinesq's influence factor is. Now, the formula for Boussinesq's influence factor. Can you tell me the formula for the Boussinesq's influence factor? Rajan, hello. There in the meeting. Okay. Not there. Okay. Okay. So the formula for Boussinesq's influence factor is 3 by 2 pi 1 divided by 1 plus r by z whole square to the power 5 by 2. Yes, it is 5 by 2. Yes. So at 0 radial distance, that is r equal to 0, 1 plus 0, 1, this becomes 1. So the value will be only 3 by 2 pi. And 3 by 2 pi will give us a value of 0.775 or 0.78. So using this particular formula, that is the formula of Boussinesq's influence factor, at 0 radial distance, if we put r equal to 0, then this entire part of this equation becomes equals to 1, and we're left with 3 by 2 pi, that is equals to 0.4775 or 0.478. Okay, next question. A circular area of 7.5 meter in diameter on the ground surface carries a uniformly distributed load of 3 kilonewton per meter square. Now, in this question, we have to first define the area and the corresponding stress distribution diagram. Now, if this is the area we are seeing from the side, then this radius, there will be a radius, and this is the vertical line. Below it is told to find below the center. This is the center, and this is 6 meter. Then this is the circular area, and this radius is how much it will be? It will be half of 7.5, that is 3.75 meter. A depth of 6 meter. Now we can solve this question by two methods. Firstly, if you see that this is what to say, this is the triangle with the height equal to 3.75, this is 90 degree, and the base is 6. We can find out the value of this angle. The value of this angle will be approximately equal to 32 degree. Okay, now the basic equation of this kind of problem is sigma, that is the vertical stress at a depth z, equals to q, that is the UDL, uniformly distributed load, into 1 minus 1 divided by 1 plus a by z whole square whole to the power 3 by 2. So using this formula, if we put Q as 3 kilonewton per meter square, if you have joined now, you can just write down from the current ongoing question. We're dealing with vertical stress distribution. Okay. So Q 1 minus 1 by 1 plus A by Z whole square. So now we place Q equals to 3 and the area that this A is the radius as 3.75 meter. And what is the value of Z? 6 meter. We can solve this question using this formula, or we can also use another formula, sigma equals to vertical straight distance Z equals to Q into 1 minus cos cube theta. Theta is this angle, that is 32 degree. Theta is 32 degree. So whatever formula we use, we will be ending up with a value of around 1.17 kilonewton per meter square. This is the answer. So we can solve this particular question by two methods. One is using the formula number 1, or using formula number 2 is the value of the internal subtended angle, half of the internal subtended angle. Q, the value of Q is 3 kilonewton per meter square, that is the UDL, uniformly distributed load, and A is the radius of the loaded area, that is half of 7.5 or 3.75. It is 3.75. I hope it is clear. I'll go to the next question. Again, a circular area is loaded with a uniform loading intensity of 100. So again, we are going to draw the diagram. Calculate the vertical pressure at a point P situated on the vertical line to the center of the load. That is like this. Same thing like before. Here it is said that the angle subtends 90 degree. So this angle subtend is 90 degree. So this is 90. So this half angle is 45 degree. Here the diameter is not given because we don't need the diameter. We are already given the angle and the value of Q. Q is equal to 100 kilonewton per meter square. Using the previous formula, formula number 2, what do we have over here? We have Q equals to sigma equals to Q into 1 minus cos cube theta. So we have, we'll write over here, sigma equals to Q into 1 minus cos cube theta. Now what is theta? Theta is 45 degree and the value of Q is 100. Putting this value, the answer we'll be getting is around 64.64 kilonewton per meter square. This is the point P. I have forgotten to mention. point P, where the entire area is subtending an angle of 90 degree. So the half angle, that is the theta in this formula, will be equal to 45 degree. Putting the value of theta and putting the value of q, that is equal to 100, we obtain a value of 64.64 kilonewton per meter square. This is the answer. Okay. Next question. A considered load of 200 kilonewton. So what is the value of the load? That is the load is q. It is considered load, we take as capital Q. It is 200 kilonewton. And there are two parts to this question. The first part, I'll just write like this. Let's divide this. In the first part, Z equals to 10 meter. And the second part, Z equals to 5 meter, and distance of R from the R will be, the value of R is equals to 2 meter. So in the first case, the value of R equal to 0, the value of sigma will be equals to 3q divided by 2 pi z square 1 by 1 plus r by z whole square whole to the power 5 by 2, and in this case the value of r equal to 0. So if we substitute the value of q with 200, z with 10 in this part, and this part will be equal to 1, then we get a value of around 0.955. Yes, 0.955. The unit is kilonewton per meter square. That is, at a depth of 10 meter below the ground surface, at the axis of loading, center line from the axis of loading, we get a vertical stress of 0.955 kilonewton per meter square. Now this same equation we will be putting over here. In this case, Z will be 5 and R will be 2 meter. At a distance of 5 meter below the ground surface and a radial distance of 2 meter from the loading axis. Putting all these values, again Q equals to 200, Z equals to 5 meter and R equals to 2 meter, will get a value of sigma equals to around 2.64. 2.64. kilonewton per meter square. So at a depth of 10 meter below the ground surface at the axis of loading, the value of sigma is 0.955 kilonewton per meter square, and at a depth of 5 meter at a radial distance of 2 meter from the axis of loading, the value of sigma is 2.64 kilonewton per meter square. I hope it was clear. I'll go to the next question. Uniform intensity of loading at the foundation level of a building 10 meter in width and of infinite length. Yes, for this question you have to again define the loading, that is, this is 10 meter in width, and then draw the center line and then join this now. We have, this is the width is 10 meters, so this is 5 meter each. At a depth of 10 meters, so this entire depth is 10 meter. We can find out the angle like this. The angle will be equals to 26.57 degree. Using simple trigonometry, 5 by 10 tan theta equals to uh, perpendicular by base. We get the value of this angle as 26.57 degree. Now the formula for this equation is, for this problem is, sigma equals to q by pi theta plus sine theta. Theta plus sine theta. Here in this case, who has joined? Yeah, sorry for the interruption. Yeah, hope I'm audible. Yes, in this case, if we take the angle as theta, this problem is a bit different from the previous problem. Why? Because we have to convert this angle into the radian. We have to convert this angle into radians. So which angle should we convert in this case? So whenever infinite length is considered and line loading is considered of infinite length, then we take this entire angle as theta, not the half. We take this entire angle as theta, and then we can say that this theta, the value of theta over here will be 53.14 degree. 53.14 degree. Now, if we want to convert this into radian, because we have to do that for putting the same in the formula, then 53.14 degree into pi by 180 will give us a value of around 0.927. So if we put everything in the formula, sine theta, that is sine 53.14 plus 0.927 over here, that is theta, sine theta will give us, and multiplied by the q is 100, and then divided by the value of pi, we will be getting a value of around 54.97. We will be getting a value of sigma of around 54.97. Hello, am I audible? Okay, we get a value of 54.97 kilonewton per meter square. So this is how we should solve this problem whenever infinite length of footing is considered. The formula is q by pi theta plus sine theta. Okay, next question. A point load of 100 kilonewton. I hope the answer was right. Yes, 54.97. Point load of 100 kilonewton acts on the ground level, maximum vertical pressure. Now we have seen in the previous question, For r equals to 1, the maximum vertical pressure can be obtained, that is sigma max at the rate z equals to how much it was? It was 1.225 meter. Now, if the radial distance is 2 meter from the axis, then given the relationship between r and z, we can say that sigma max will be obtained at the rate z equals to twice this value, that is 2 into 1.225, that is equals to 2.45 meters. Now, to find out the value of the sigma, there is a maximum vertical pressure, maximum vertical stress or pressure in this at this depth. Use the usual formula 3q by 2 pi z square 1 divided by 1 plus r by z whole square whole to the power 5 by 2, where r will be equals to 2 meter and z will be equals to 2.45 meter. Q, the value of Q is 100. Putting all these values in its usual places, appropriate places, we get a value of around 2.22 kilonewton per meter square. 2.22 kilonewton per meter square. This is the answer. So to find the maximum vertical pressure, to find the distance from the ground surface at a depth at which the maximum pressure would occur, it use the equation r equals to 1, sigma max will be at z equals to 1.225. Like that, if r equals to 2, sigma max will be at z equals to 2 into 1.225. And then using the value of r and z and q given in the question, to find out the maximum vertical stress. I hope it was clear. I'll go to the next question. A concentrated load of 50 kilonewton acts vertically. Compute the ratio of vertical stress at depths of this and this. Okay. So, as we have seen in the formula, stress is inversely proportional to the square of depth. Stress is inversely proportional to the square of depth. So, we can say that sigma 1 by sigma 2 will be equals to, the ratio will be equals to z2 by z1 whole square. Now, in this case, sigma 1 means sigma at a depth of 3 meter and sigma 2 means sigma at a depth of 5 meter. That will be equals to z2 is 5 and z1 is 3 whole square is equals to 25 by 9, it will equals to around 2.78. I hope it was clear. We have to use a simple basic relationship between sigma and z, that is sigma is inversely proportional to the square of depth. Okay. I'll go to the next question. Yes, a rectangular area carries a UDL. So if this is the rectangular area, 2 meter by 4 meter, this is 2 and this is 4, it carries a UDL of 8. So in this question, we're going to convert the UDL into a point load. How can we do that? We can do that by multiplying the UDL with the area. So Q will be equals to UDL into area. That is 4 into 2, 8 into 8. That will be 64. I repeat once again, the UDL will be multiplied with the area to obtain the equivalent point load. Now, we are asked to find out the stress at the corner, and for that, what we have to do is we have to find out the radial distance of the center from the corner. So this will be 1 half of 2, this will be 2 half of 4, and this radial distance r is going to be equals to root over of 2 square plus 1 square, that is root over of 5. That is root over of 5. In this case, we are going to again use the same formula, that is sigma equals to 3q divided by 2 pi z square 1 divided by 1 plus r by z whole square whole to the power 5 by 2. Now below the center, r will be equal to 0, and at the corner, r will be equal to root over of 5. Z will be equals to 5, q will be equals to 64. And in this we can find out two answers, that is directly below. For directly below the center, the equation will become like this: 3q by 2 pi z square. Okay, and that will be equals to, because r is equal to 0, this is equals to 1, that will be equals to approximately okay, this load will not be in kilonewton, this load will be in the unit given in the question, that is in ton T. The answer will be also in ton per meter square, 1.22 ton per meter square. And for the second part, that is a corner with r equals to root over of 5, z equals to 5, and q equals to, as given, 64 ton, we get a value of around 0.77 ton per meter square. I hope the solution was clear. We are going to convert the UDL into equivalent point load by multiplying the UDL with the area of its action, and then we are going to calculate the radial distance of the corner of the loaded area from the center, and then we are going to put the values in the formula, Boussinesq equation formula: 3q by 2 pi z square 1 by 1 plus r by z whole square root to the power 5 by 2, and by that you can get the value of the vertical stress at two positions, that is below the center and the corner of the loading area. Okay, next question: the vertical stress at some depth below the corner of a 1.5. Okay, so firstly the vertical stress is given 1 by 1.5, that is, this is 1 and this is 1.5, like this. This is 1 and this is 1.5. Below the corner, that is at this point, suppose this point is P, vertical stress is 100. So sigma p equals to what? Sigma p is 100 kilonewton per meter square. Now, what is the vertical stress below the center of a 2 by 3? So if we observe carefully in this question, we can see that the geometry of the area which has been given and the geometry of the area which we are told to find out is exactly the double. That is, the one which is given is exactly the half of the one which we are asked to find out. So if we extend this area, like another one we place over here, and extend this area, another 1.5 we place over here like this, and then make it a full rectangle, then we'll be obtaining this area which is being given in the second part of the question, that is another one and another 1.5, that is 2 by 3 meter rectangular footing at the now uh, rectangular footing, yes. Now if for one of this block the intensity of vertical stress at the corner, that is this P point, is 100, then for four blocks, that is all these blocks combined, will exert a vertical stress at this point P equal to 4 times of 100, and that pressure is acting at the center of this final loading area. So to find the final uh, vertical stress of the modified loading area, modified rectangular footing at a point P, all we have to do is combine the vertical stress at the corner of each individual slabs of 1 by 1.5, that is 4 into individual stress of 100, that is we get a value of 400 kilonewton per meter square. This was a tricky question. There is no need of any kind of Boussinesq or any kind of formula over here. We just have to multiply the given magnitude of stress with the number of original blocks or the original footing dimension, original number of footings of the number of footings of the original dimension to obtain the vertical stress at the center of the modified footing. I hope it was clear. Okay, next question. So we now have covered up the entire Boussinesq theory. Next question: intensity of radial stress in ton per meter square at a point 4 meter directly below a 2 tons point load. This is also a tricky question because directly below, that is, if this is the load and this is directly below at this point P, there will be no radial shear stress because the value of R equal to 0. The value of R equal to 0, so there will be no radial shear stress, so the value is 0 at exactly vertical from the point of action of force. The radial distance is 0, so the value of radial stress is 0. Next question: the Newmark's chart is based on, the very important question, the Newmark's chart, that is division of the circular area into number of annular rings and the number of sectors, that is based on the Boussinesq theory, original Boussinesq theory. Next question: what is the type of foundation? Yes, in this question we can see that the settlement is uniform but the pressure distribution is not uniform. Whenever the settlement is uniform, that uniform settlement symbolizes or signifies a rigid footing. Uniform settlement signifies a rigid footing type of foundation. Now, the contact pressure. So, if the contact pressure is such that it is very low at the center and high at the corners, then that signifies cohesive soil or clayey soil. So, in this question, the type of foundation is rigid and the type of soil is clay because it is giving a vertical pressure which is maximum at the corners or at the edges and minimum at the center. Rigid footing in clay soil. Now, in the construction of Newmark's chart, the number of annular areas. Yes. So, if you refer to any standard book of soil mechanics, you will have to find out that in Newmark's chart, the entire area is first divided into a number of rings or annular areas and then divided into number of sectors. The value of influence factor is each individual sector of this chart, that is IF influence factor. So each individual area will be total area divided into, at first divided into 10 annular rings, and then each annular ring is divided into 10 sectors. So the value will be equals to 1 by 100 or 0.01. Entire area is divided into 10 annular areas and each annular area is further divided into 10 sectors. So the influence factor is 1 by 100 or 0.01. Next. Originally, the number of sectors considered in the Newmark's influence chart is. Now, in this question, it was asked that it was 10 sectors. But originally, 10 number of annular rings is being considered, with each annular ring being divided into 20 number of sectors, for which the influence factor we get in the original Newmark's chart, the entire area divided into 10 number of annular rings and each annular ring or annular area is divided into another 20 number of area units or sectors. We get a value of 1 by 200, that is 0.005. This is the value of the influence factor which we will be utilizing in the upcoming questions of numericals using the Newmark's chart. So this number of sectors, the answer of this question is 20. Originally, that is in the original Newmark's chart, 20 number of sectors of each annular area is being considered. Now, next question. Yes, another question where settlement is uniform. So settlement is uniform, that means it is a rigid footing. And here the soil is giving maximum pressure at the center and minimum pressure at the corners or the edges. So according to the pressure, we will be saying that this is sandy soil or cohesionless soil. Rigid footing on a sandy soil. Next question. Here the question is different from the previous question because we can see that in this case the pressure distribution is uniform. When the pressure distribution is uniform, then it goes without saying that the footing is flexible. It is a flexible footing because in place of flexible footing, the pressure distribution is uniform, but a flexible footing will not show uniform settlement. It will show non-uniform settlement. And for this non-uniform settlement, if the settlement is maximum at the center and minimum at the edges, then we can say the type of soil is clay soil. Because of the settlement is not uniform and settlement is maximum in the center, the type of soil is clay soil. So it is a, this diagram signifies a flexible footing on top of a or in a clay soil. I hope it is clear. Okay, next question. A rectangular area 3 by 1 meter is uniformly loaded with load intensity of 100 kN per meter square at the ground surface. Newmark stat. Yes, at a point 4 meter below. We could have done this question using the Boussinesq theory, but using the Newmark's influence chart, the formula we have, that is the stress, vertical stress sigma is equal to Q into IF into NA. The value of IF, as I have told in the previous question, will be taken as a generalized value, that is influence factor equal to 0.005. 0.005. Na equals to 12 and Q, the value of Q is 100. Using all these values, we can find out the value of the stress. Now, in this case, we are not considering 4 meter below the corners, because for 4 meter below the corner, the Newmark's influence chart gives the number of sectors is Na equals to 12. So, irrespective of the point, if we find out the Na from the chart, which has been already mentioned over here, then we can put directly in this formula and find out that the answer is 100 into 0.005 into 12 will give us a value of 6. Yes, 6 kilonewton per meter square. Okay, I hope it was clear. Next question. I think they have left the meeting. Okay, next question. Last question. Again, type of foundation. This is a uniform contact pressure, uniform pressure distribution of the contact. So again, this is going to be a flexible footing. Now, in this case, the settlement is minimum at the center and maximum at the edges or the corners. So, this kind of soil is cohesionless or sand. So, the previous one was flexible footing on clay, and this one is flexible footing on cohesionless soil or sandy soil. So, in this case, using the pressure distribution and type of settlement, we can find out the type of foundation and the type of soil. Okay, I hope it was clear. So, thank you whoever joined the discussion. Have now left. Okay, I'll be ending the session now.